Hello, everyone. Welcome to this year's edition of ZuriHack 2011. You read the slides?
There we go.
Yeah. Welcome again.
Yeah, hi everybody. We will keep it short because you're all here to see John Hughes. Just some quick notes to how the event will work in case you haven't been here last year. So basically, most of you should already be in Discord. That's our hub. That's where if you stay there, you will not miss anything. So we'll have we are having a lot of project channels. We have an announcement channel where you will be pinged every time we announce the next talk or something like that. If you need any help, just write us in help desk or ping organizers. And yeah, that's also going to be where the talk discussion will take place. The only other thing we're using is YouTube and to stream the talks and stream some of the tracks. There's a schedule on our website. You can check that one out. We'll show it to you in a minute. Just like some quick notes, the schedule looks kind of full for a hackathon where you're supposed to just hack. It looks like it's a conference. It isn't. Like the main event is still you join your friends or like you're not yet friends, but future friends on projects. You code, you learn, you just enjoy yourself. Don't be afraid to miss out on anything. We made sure to not have too many things in parallel. And the things that are in parallel are usually between beginners and advanced people. So yeah, and yeah, just watching announcements. We usually will try to ping everybody 10 minutes before something important happens. So yeah, this is basically the overview. So there will be project channels. You can pitch your own project to get people to help you out on that. You can join one of the tracks. You don't need to register for that. And you can also do impromptu presentations. Basically, anything you want to do is probably fine. Afterwards, we will also have a couple of sessions with partner companies. They are also on the schedule, as you will see. And because everybody's complaining about never finding a Haskell job, there's like chances that a lot of them will be hiring. So you can talk to them, ask them about their industry. And otherwise, I don't know, if you're a social person, go talk to everybody. If you're more shy, just lurk around, see what you can learn. Most importantly is that you enjoy yourself.
Hey everyone. So since we have a virtual event again this year, we try to change up the program a little bit, and you can see there's a lot of stuff. So this is the schedule for the coming 3 days. Obviously, as Yuri said, you don't need to attend every little thing. You can just still hack on project and just socialize and hang out in the hallway track. So to be sure, you can view this schedule on zurihack.com, and there's also a link to a Google Calendar there, so you can add it on your phone, and then you can kind of see it in your time zone and get reminders and so on. So in the schedule, we have talks, and John Hughes will give the first one just after this opening ceremony. There's sort of a color coding, and we have presentations by various companies that are light green. We have obviously the talks that we invite everyone to attend in dark green. And then we try to distinguish between events that are geared a bit more towards beginners in light yellow and events that are geared towards a bit more advanced users in dark yellow. But obviously, feel free to attend anything that you are interested in. Next slide, please.
So how do you ask questions during our talks? You have to go to our Discord channel, #talkdiscussions, that Yuri already has said, and we will read the questions during the talk on the live stream. If there are many questions, you might need to upvote a few of them, so we ask them to the speaker. Next one. And some few tips if you're a bit confused. There are a lot of channels, so you can use Ctrl-K or Command-K to go to them quickly. And you can collapse or mute them if there's just too much of them. And use settings, the button. You can do a lot of things like turning on or off the notifications, testing your voice and your video, or simply change your appearance.
So obviously, the 4 faces you see right now, we are not the only organizers of ZuriHack. We received a lot of help from different volunteers, and obviously we wouldn't be anywhere without our speakers. So a big thank you to all of the people who helped us out.
This year, we did not need much sponsorship in terms of money, being an online event, but these organizations supported this year's ZuriHack in other ways. They will have some company-specific channels, so check out what they're doing.
That was it. Thank you for attending our very short opening ceremony, and then we will now resume with the talk by John Hughes. Farad?
Yeah. So would you like to put up your slides, John?
Okay.
Sure. So while John is fixing up his slides, so John Hughes works in both academia and at Chalmers in Sweden and in industry at QuickCheck, as well as being an ACM fellow. But I guess everyone already knows John from his work on property-based testing using QuickCheck. This is something that is not only used in the Haskell world, but has been ported into many other programming languages. We are really honored to have him as the opening speaker at ZuriHack 2021. Thanks for being here.
Okay, thank you very much. So let me see if I can find my view. Yes. Okay, so hello, Haskellers. I had asked in advance to find out how many of you are QuickCheck users, and I think the answer was about 60, 70%, something like that. So what I'm going to talk about today is some recent work that we've been doing on testing smart contracts with QuickCheck. And my focus is going to be partly on the application, which is an exciting one, but also on some of the things that you need to know when you're using QuickCheck effectively in a more complex setting than the simple examples. And one of the things that I learned was we came up with some new ideas while developing a smart contract testing framework, which I think are going to have much broader applicability. So I'm quite excited about those as well. And I'm going to cover those new ideas in this talk as well. So I just want to say, do feel free to ask questions as we go along. If you type them into the channel, then Farad will interrupt me. And I would much rather answer questions during the talk and have you follow me than leave something misunderstood for a long, long time. So feel free to do that. Okay, so I'm going to talk about testing smart contracts, and I should start off just by explaining briefly what a smart contract is. It's basically a small program that runs on a blockchain and ensures that transfers of cryptocurrency are according to the terms of the contract. Smart contracts originate from the Ethereum blockchain. That was Ethereum's unique selling point, that it could offer these smart contracts. And as a result, it's the second largest cryptocurrency today. But of course, one of the problems with giving a program control over money is that bugs in the program can result in money being lost or stolen. And there have been many, many examples of Ethereum contracts from which money has been stolen. Just to take one of them, there's the well-known DAO attack in 2016, which was an attack on a crowdfunding contract, in which the equivalent then of $60 million of Ether was stolen. So when there are bugs in contracts, that can result in tens of millions of dollars being stolen at a time. So it really is important to test them thoroughly. Now, I'm not going to talk about testing Ethereum smart contracts. I'm going to talk about testing contracts for these guys. This is the web page of a company called Input Output that you might be aware of. They run the Cardano blockchain that supports the ADA cryptocurrency. What is Cardano? What is ADA? Well, when I was preparing this slide, I copied the market cap of some of the world's top cryptocurrencies. The market cap is the value of all of the coins put together. So at the time I made this slide, then all Bitcoins put together were worth around $1 trillion. The second largest cryptocurrency was Ethereum, and the total value of all Ether was about $1/3 of $1 trillion. On that day, Cardano's ADA currency was worth a total of $43 billion. So much less than Bitcoin and Ethereum, but that was still enough to make Cardano the world's 7th largest cryptocurrency. And since then, Bitcoin and Ethereum have dropped a bit and Cardano has gone up a bit. So today it's the world's 5th largest cryptocurrency. And there are hundreds or thousands of cryptocurrencies. So being number 7 or number 5 is makes them one of the top ones. But Cardano is interesting for several reasons, not just that it's one of the large cryptocurrencies. It's the largest cryptocurrency that uses a proof of stake consensus algorithm. So you may know that Bitcoin uses more energy than some small countries to mine its blocks and perform its transactions. And that is because Bitcoin uses a consensus algorithm called proof of work, which is, it was a very clever idea, but it's inherently wasteful. And that has resulted in enormous amounts of energy being consumed to run Bitcoin. And most cryptocurrencies work the same way. But there is an alternative, and I think the most principled alternative is to use proof of stake consensus instead. And the Cardano blockchain is the largest one that does that. And that makes it at least 10,000 times more energy efficient than Bitcoin. So I would say that proof of work is clearly not sustainable, with the climate crisis upon us. But Cardano is. It's the largest sustainable cryptocurrency. That makes it very interesting. The other interesting thing about it is that Cardano uses Haskell. Both the blockchain itself is implemented in Haskell and the smart contract language is based on Haskell. So one may hope that writing smart contracts in Haskell may, with luck, contribute to making them a little bit less buggy. But of course, they still need to be tested. If you look at the Cardano documentation, you'll see that their contract language is called Plutus, and it's not running in the blockchain itself yet. I believe Q3 this year, they're supposed to introduce smart contracts for real. But you can experiment with Plutus in what's called the Plutus Playground. And all of the documentation is online. And part of that documentation is this tutorial on property-based testing of Plutus contracts. So Input Output hired us to develop a property-based testing framework, and that's what I'm going to tell you about today. So of course, if we're going to test smart contracts, we want to test them with QuickCheck, and hence, that's why they asked us. So I should tell you a little bit about the Cardano blockchain and the way its smart contracts work, because they're rather different from the way Ethereum smart contracts work. The blockchain is basically just a list of transactions. So people submit transactions the whole time, and then every 20 seconds or so, a bunch of them are collected and they're put into the next block on the blockchain. And the blockchain history tells you what has happened in the past. Every transaction generates some outputs and consumes some inputs. And the inputs are the outputs of previous transactions. So in fact, all of the money on the Cardano blockchain is represented as transaction outputs. And since you can only spend a transaction output once, of course, then the actual money is represented as unspent transaction outputs, or UTXOs. And that is the same way that money is represented on the Bitcoin blockchain. Now, one difference between the Bitcoin blockchain and Cardano is that Cardano supports what are called extended UTXOs, unspent transaction outputs. And what the extended means is just that the transaction output contains not just an amount of money, but a bag of tokens. It can contain tokens of different types. So the Cardano blockchain supports user-defined tokens natively. Now, a transaction consumes inputs and generates outputs. And of course, the sum of the outputs has to equal the sum of the inputs. This is an invariant that the blockchain enforces. You can't conjure money out of thin air. Unless, of course, you conjure money out of thin air, which you are also allowed to do by forging new tokens. But the sum of the outputs must equal the sum of the inputs plus whatever you forge. That's always checked by the blockchain. But of course, there are many other constraints on what a transaction can do. You can't spend somebody else's money, in particular. And to guarantee that you don't do that, every transaction output has a function attached to it. And you can think of it as a function from transaction to bool. That's not quite the type, but in principle, that's what it does. And that function is provided by the owner of the transaction output. And before a new transaction is allowed to spend that output, then the verifier gets called. And it has a chance to inspect the spending transaction and decide whether or not it looks okay. So when you submit a transaction, the blockchain will call the verifiers of every output you're trying to spend. And if they all return true, then your transaction can be added to the blockchain. Now, I mentioned forging new tokens as well. There's another kind of function that makes sure that you follow what's called the monetary policy for forging. So that's also restricted. You can't just manufacture money arbitrarily there either. So on the Cardano chain, these functions are written in a language called Plutus, which is a subset of Haskell. And in fact, it's compiled using GHC and then extracted from the code that GHC generates. And this is code that is run by the blockchain itself. So we call this on-chain code. And it's run to inspect transactions and make sure that they're not violating contracts. But before you can submit a transaction to the blockchain, you also have to construct it. And that's a bit of an art too. So that is also done using Haskell code. And so it's this Haskell code that we will usually think of as the smart contract on the Cardano blockchain. So a contract really is a combination of off-chain code and on-chain code. The on-chain code is Plutus, and it's run by the blockchain itself. The off-chain code is Haskell, and it's run in your wallet. And a wallet is just an application that you run on your own computer. So it's this combination of off-chain and on-chain code that has to work, and that's what we want to test. Okay, so we wanted to figure out how to test these smart contracts with QuickCheck. Well, many of you are familiar with QuickCheck. Some of you use other property-based testing tools like Hedgehog, and so you will have seen properties. I'm sure you've seen this one, for example. Right, this is the QuickCheck Hello World. It's the property that checks that if you take a list and you reverse it and then reverse it again, you get back where you started. So for those of you who haven't used any property-based testing tool, this is just a function that takes a list of integers x's, that's the test data, and then performs the test using that data. And what QuickCheck does is generate random values for the parameters of these properties. So it'll generate random lists of integers, and then call the function and check that the property holds in every case. So this property very often appears in introductory talks on QuickCheck. And many of you will have written properties of this sort yourselves. Maybe a bit more interesting than this one, here's another property that is similar in spirit. This is a property for testing insertion into a map. And if you look at it, you can see, let me get my pointer, that we're taking two key value pairs and a map that is called T in this case. And what the property says is that if you insert both key value pairs into the map, you get the same result as, okay, well, what you get depends on whether the two keys are the same or not. If they're equal, then the first insertion is essentially discarded. So you just get the same as you get by the second. But if they're different, then it doesn't matter what order you do the insertions. You get the same map in both cases. So that's a property that hopefully is quite intuitively true. And it's also quite a good test of an insertion function. And in fact, both of these properties come from a paper of mine called How to Specify It, which was a tutorial paper that I wrote about how to write properties and test them with QuickCheck. And you can find it online. So if you aren't a big QuickCheck user, then I would recommend that to you. But properties like this, which I think are fairly common, they're quite restricted. It's easy to write properties of pure functions, like reverse or insertion into a map. And that's the kind of functions that this kind of property can test. But also, these properties have a fixed structure. And what I mean by that is that every time you test this property, you're going to be doing the same set of function calls. Right? The only thing that varies is the data that you're testing the functions on. And that makes these kind of properties quite simple to write, easy to use. But when we test smart contracts, we're going to need something else. So the thing is that smart contracts have a state that gets updated as you submit operations to them. They have what are called contract endpoints. That's what these blue things are supposed to represent, which is the API of the contract. And when you invoke a contract endpoint, then that is expected to change the contract state. So invoking these endpoints has side effects. And we don't want to write properties now that perform a fixed sequence of calls. Because the interesting thing when you're testing this kind of software is to find sequences of calls that provoke quite unexpected errors. So what we want to do here is to generate not just the data used in the test, but the structure of the test itself. And this is something that we always need to do, basically, when we're testing stateful software like smart contracts. So the smart contract, as I said, it runs in your wallet, and then it talks to the blockchain. And what we're going to do is we're going to generate random sequences of actions using QuickCheck that are going to be our test cases. And then we're going to perform those actions in sequence. And when we perform an action, it's going to invoke an endpoint. And the endpoint may send a number of transactions to the blockchain where they get inspected by the Plutus code, and the blockchain decides whether or not to accept them. And then after performing one action, we'll perform the next action, and so on. And at the end of the test now, we need to know, did the test pass or not? And to determine that, we're going to look at the contents of the wallets. So basically, the whole purpose of contracts is to move money around. And so if the money always ends up in the right place, then the contract is working. That's what we care about. And so that's going to be the test oracle that tells us whether or not a test has passed. Now, how will we know where the money should end up? Well, to do that, we will build a model of the contract state. And then for every action, we'll define the state transition function on that model state. And the model will tell us at the end of each test where the money should be. So this is the approach that we have used for building a test framework for the contracts, and it's the same approach that we have used for many, many stateful systems. Now, when a test fails, it's usually because of only a few actions in the sequence. So QuickCheck users will know that QuickCheck does something called shrinking. After a test fails, it searches for a smaller but similar test that also fails. And especially in this kind of situation where the test cases tend to be long random sequences, it's really, really important that shrinking works well. Because usually when a test fails, it's because of only a few actions in the sequence, and shrinking identifies those and produces a much smaller test case that only does relevant things to provoke the failure. So you're going to see a lot of failed tests during this talk. And I want you to remember that in every case, they are the result of shrinking. The reason that the framework gives you small, simple examples showing what went wrong is that shrinking has simplified a much more complex random example down to something that is salient and to the point. So these state machine models that we're going to use, as I say, we've used the same general approach for a long time. I have given a talk called Testing the Hard Stuff and Staying Sane, and I've even written a paper with that title. So if you would like to read more about this approach in general, then I recommend my paper to you. We implemented this for the first time in Cubic, our company's version of QuickCheck, in Erlang. But nowadays, there are state machine modeling libraries for many property-based testing tools. So there's one for QuickCheck on Hackage called QuickCheck State Machine. We haven't actually used that in this project. We've used one in the Plutus code base, Plutus contract test contract model. And that's the one that I'm going to be using today. But a lot of what I'm telling you about testing with state machines will apply no matter which property-based state machine modeling library you use. So I want to talk about testing a contract, and to do that, I need an example to talk about. And the tutorial that I mentioned is based on an example from input-output, which is a simple guessing game. So let me just explain how this example works to you. The game starts when some wallet offers a prize. And that is done by locking the prize money in a contract on the blockchain, protected by a secret password. So this little icon here is supposed to represent 14 ADA in prize money that are locked in the contract, and the password is the word secret. Okay, so once the contract has locked the prize money, then other wallets can play the game. And the way that a wallet plays is by submitting a guess. So in this case, the wallet on the top right submitted a guess asking for 5 ADA in prize, so you can say how much you want to withdraw. But the wallet guessed that the password was the word secret, which is not the same as secret, and thus the guess failed. No prize money is won. Eventually, presumably a wallet will guess correctly. And when that happens, and a correct guess is submitted, then the submitting wallet can withdraw the money that it asked for. And also, the password gets updated to a new password chosen by the wallet that guessed correctly. So now the wallet on the bottom right is the one that knows the secret password. So it's a very simple game, but it illustrates making contract transactions and so on. Now, we're actually going to make it very slightly more complicated. And the extra wrinkle is that when the first wallet starts the game, it's also going to forge a new token. And this is of a special currency whose only purpose is playing this game. And there will only ever be one coin of this currency. We call it the game token. What is it for? Well, the idea is that in order to submit a guess, you must be holding the token. So we can restrict who can play by passing the token around. So you can think of the token as a way of restricting who is allowed to play. I think its real purpose is, as an example, to illustrate how you forge new tokens using the Cardano blockchain and the smart contract framework. Okay, so this is the game that I'm going to show you how to test. So remember, I said that we're going to generate tests that are lists of actions. So what are those actions? How do we define those? So the way that our framework works is that we have defined a Haskell class that QuickCheck knows how to test for representing contract models. And you define your test just by defining an instance of this class. So the first thing that you have to do when you define your particular instance, in this case it's the game model instance, is to tell QuickCheck what kinds of actions you want to include in your tests. And in this case, you've already seen the actions in my little animation. First of all, we want to be able to lock the prize money. So this is done when we start the game. And then wallets are going to be making guesses. And we also need to pass the token around. So we'll have a give token action as well. And then in each case, the action contains the wallet that should perform the action in the tests. And the secret passwords are strings. And the amounts are integers in this case. So those are the actions that we're going to include in tests. And then, as always using QuickCheck, we need to specify how to generate test data. And in this case, QuickCheck knows how to generate those test scripts, but we have to tell it how to generate this action type. And so here is the code for doing that. So how do we generate an action? Well, we use QuickCheck's API to say it's going to be one of these three alternatives. And then what I've done is I've just made use of separately defined generators for wallets, guesses, and values. And then I'm just choosing uniformly between generating a lock action, a guess action, or a give token action. So once you define that, then QuickCheck can generate test cases for these contracts. There's a bit more work to do to enable QuickCheck to run the test cases, to connect it to the actual contracts themselves. But I want to focus on how we do the modeling. So let's just think informally about how we might model the behavior of a guess. Okay, so when a wallet submits a guess, then in order to decide what will happen, the test code needs to know whether or not the guess should succeed. Right, so when does a guess succeed? Well, for a start, the secret password should be guessed correctly. Secondly, the wallet must hold the game token, remember? Thirdly, we'd better be asking for an amount of money that is actually locked by the contract. Otherwise, it can't possibly work. But if all these conditions are true, then what should happen? Well, the wallet making the guess should get the amount that it requested. The password should be replaced by the new one from the guess action, and the amount locked in the contract should be decreased.
John,
so if
may I just interrupt you quickly? There are some questions on the channel.
Okay.
The first question is that it refers to the previous slide. So there's about a 20-second pause between questions.
Sure,
so
yes.
It's from the previous slide. So is that data declaration valid Haskell? I can't see how data action game model works. This is the first question.
Okay, so when you define a Haskell class, then such as contract model here, then usually you will see that you define a number of methods in the class, which are usually functions. But you can also include types in a class. This is what is called an associated data type. So yes, it is valid Haskell as long as you turn on the right option when you're compiling. And what it means is that every time we define a new instance of this contract model class, And here I'm defining an instance for the game model type that we'll see in a moment, in a short time. Then I can define a new type of actions that is associated with this particular instance. And that type is called, well, action with a parameter. And this parameter has to be the same as the class parameter or the instance parameter up here, right? So the type action game model is a type of actions that will be referred to when we use the game model contract model. Okay, so this means that every time you define a new contract model, you get to choose a new type of action. And of course you need that because depending on which contract you're testing, it'll have a different API. And this type here is just representing as a Haskell type the API of the contract that we're trying to test.
Great, thanks. Second question, in arbitrary action S, what does the S parameter represent?
So we model the state contract. So there is a model of the state in all the functions that I'm going to show you. And that model state is passed to the arbitrary action generator. So we don't need it in the code on this slide, but what it means is that when you write a generator, you can take into account what the current state of the contract is. So you're generating an action for a particular place in the test case. And as you're generating that action, you know what the model of the contract state is at that point. We'll see that used in a short time. So I was trying to gloss over that a little bit, but you caught me out.
Yeah. So there's a third question. Is there any work on making sure that the generator covers the input space well?
I will talk about that a little later on. Can I just postpone that question for now? It's an important question.
Good. Thank you. I'll remove myself now.
Okay, great. So let me go back to the slide here. So I had just gone through an informal explanation of how we might hope to model a guess. And I just want to look at this informal text in a little bit more detail. And you'll notice that parts of it, the parts that I've colored blue here, talk about the contents of wallets. And every time we model the behavior of a smart contract, we're going to need to talk about wallet contents because wallets and their contents are fundamental to the behavior of a smart contract. So that's something that should really be a part of the testing framework because it's always going to be the same. But other parts are talking about this particular contract, right? So when we say the guess is correct, the game contract, has a guess, has a secret password, but most other contracts may not. So a part of what we need to talk about in the model is going to be standard stuff, wallets and the contents, and a part of it is going to be specific to the particular contract that we're modeling. And if we look at the red text here, we can see what information the contract model has to give us, right? So we need to be able to decide whether a guess is correct. That means our model of the contract state must tell us what is the current value of the password. We're going to need to compare the amount requested to the amount that the contract should be holding. So the contract model is going to need to keep track of how much is locked by the contract at the moment. We're also going to need to know where the game token is at the moment. Remember, only one wallet can have it at a time. So when we write this kind of model, one of the key things to do is to define this contract state. And this is the code that we use for modeling the game contract. So this is the game model type that we're defining the instance for. And you can see that it has 3 components here. We're going to keep track of the value of the game. That's an integer number of ADA. We're going to keep track of where the token, the game token, currently is. And of course, at the beginning of a test, before we've started the game, there is no game token. And that means that if we're tracking its location, well, there might be no location. And that's why this has token field is a maybe wallet. Okay, so either just a wallet or nothing at the start. And then finally, we're also going to track the current value of the secret, which is just a string. Now, you'll notice that all these names start with underscores. That is because we're using the lenses library here to make lenses for accessing these fields. And you will see that in use in the rest of the code that I show you. So now, how do we model the guess? Well, we define another method of that contract model class, the next state method. And I said that we would define a state transition function. This is how we do it. So here I'm just showing one clause of the next state function that defines how a guess changes the contract state. And if you look at it, you can see it's monadic code, and it corresponds very closely to the informal text that I wrote up above. Okay, so what's happening? First of all, we're viewing the contract state using the current secret lens. So this current secret was generated by the make lenses on the previous slide. So we're looking at the current value of the secret. We're comparing that value to the guess at the old value from the guess. And if they're equal, then the guess is correct. Correct guess is a Boolean. And we need to check, does the wallet submitting the guess, that's W, hold the game token? So we look at the contract state again. We see who has the token. We say, is it just W? If so, holds token is true. And likewise, we look at the game value and compare it to the value that we're asking for and see, is there enough ADA? And when all of those conditions are true, then we do the action corresponding to these things here. So what are we doing? Oh, I put them in a different order. That was stupid. Oh, well. So we're updating the current secret to the new value from the guess. We're subtracting the value being withdrawn from the game value, and we're depositing money corresponding to that value into wallet W. So here, this deposit is actually the standard part of the contract modeling that models putting something into a wallet, whereas these other parts are specific to this particular contract. It's important to remember that this is the model state transition function. So this deposit here is not doing anything on the blockchain. It's just updating the model to record the fact that we expect this value to be placed into wallet W as a result of this operation. Okay, so now I could go on to write next state functions like this for lock and give token as well, and then I can run tests. Okay, so what happens when we do? Well, I just call QuickCheck from GHCI, and I give it the game property. I haven't shown it to you, but it's a standard property provided by the framework. And ta-da! The tests fail. So in this case, first I ran these tests, I got an exception, maybe from just nothing. The actual test case is here. So if you look at this, this is the list of actions, and there's a tag on it as well. You can ignore that. So what is the test doing? All it's doing is trying to give the game token to wallet 1. And you can see that failed with an exception. So I just want to emphasize, look, only one action is happening here. The original generated test will have had a bunch more stuff in it. I don't know what. But after 3 random tests and 3 shrinking steps, then we ended up with this single test that just does the relevant thing. So we've got a test that just tries to give the token to wallet 1. And we've got an exception involving the maybe type and a nothing value. Where is the maybe type coming from? Well, this is how I define the has token field in the model. Right? It's a maybe wallet. And what's happening here is that we're trying to give the token to wallet 1. That means we need to know where it is at the moment. And where is it? There is no token. We haven't started the game. So of course, we can't do this. of course this test can't work. In fact, this test fails just when we try and run the model. We don't even need to run the contract for this to fail. And the reason it fails is that we're trying to give the token to a wallet when there is no token. So it's a stupid test, basically. And this is something that happens a lot when we test APIs that are stateful. Almost always when you use a stateful API, there are some rules about how you're supposed to use it. And there are some sequences that will just make no sense. And so we have to have a way of telling QuickCheck that this is a stupid test. We don't want to generate this test. How do we stop QuickCheck from doing it? What we do is we supply a precondition. And our framework lets you give a precondition for each action. So for the give token action, it's going to be simple. It's just going to say there must be a game token. Otherwise, you can't give it. And that gets specified by writing a precondition callback that is another member of this contract model class. And you can see it's given an action and it returns true or false. And if it's a give token action, then it looks in this contract state that you asked about a few slides ago and uses the lenses to extract the has token field. That's what TOC is. And that must not be nothing. It must be just something. So the token must exist somewhere for give token to be valid. And the other actions, they just have a true precondition. So what happens when we define a precondition like this is it tells QuickCheck what the valid tests are. And now QuickCheck will not generate any test in which the precondition is not true, which means that test that failed on the previous slide can no longer be generated. And so that's fine. We'll generate more sensible tests. Let's see what happens when we run tests now. Da-da! Oh, failed again. So here's the next test case that failed. And if you look at it, you can see that QuickCheck has generated a test that is also rather stupid, right? Because here, wallet 1 is starting the game twice with 2 different passwords. And now it should be clear that this must lead to a problematic situation, right? What should you guess to get the money out when the 2 passwords have been supplied? So it's clearly a bit problematic. But what actually happens is that the contract crashes. The off-chain code crashes. And if we look through the output that appears, there's quite a lot of it, but somewhere it says, found 2 outputs, expected 1. So what's happened here is we actually ran this test against the contract, but when we lock the contract, the off-chain code submits 2 transactions. It submits one transaction paying the prize money to the contract script, and then another transaction telling the contract script to move to the locked state. And when we do that for a second time, then the on-chain code says, oi, 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 the contract is already locked. You can't lock it again. And so that second transaction is rejected by the blockchain. And now we've got 2 transactions, both of which are sending outputs to the contract script. And the contract doesn't know how to deal with that. So it says, found 2 outputs, expected 1. And in fact, at this point, if you were running this for real, you would now not be able to recover your money from the contract using the existing off-chain code. So this is kind of an interesting example, I think, because if we look at the test case, starting the game twice, it's obviously stupid. And yet it's something that somebody could do. So here's the question for you. Is it a bug or not? Is it a bug in the contract or is it a bad test? So I would probably argue that somebody might in reality do this, and you don't want to end up crashing your contract and in a situation where you might have difficulty recovering the money. So I would probably say this is a bug. But you can imagine what would happen if you were to take this bug, to another developer and say, hey, your code doesn't work. Look, it fails in this case. And the other developer is quite likely to say, well, don't do that then. And this is something that we quite often find in this kind of complex situation, that QuickCheck will generate a case that maybe nobody thought of. And then there may be disagreement about whether it's a bug or not. Anyway, at this point, we can't run any more tests sensibly without doing something about this problem, because QuickCheck will find this problem every single time. And what we can do, of course, is write a precondition for lock. So if the developer says, don't do that, it's stupid, we can tell QuickCheck, don't do that. And we do it in the same way that we avoided giving a token when no token existed. We write a precondition that says you can only do a lock when there is no game token yet. And so when we start a test, there is no game token, we can do a lock. In fact, we'll have to. And once we've done one lock, there is a game token, and so QuickCheck will never generate a second. And that means that that problematic example that we just saw will never be generated again. Okay, so this is something it's important to bear in mind, that preconditions quite often get used in this way to work around bugs in the software under test and to enable us to run more tests. Now, maybe in the future, we or somebody else will come back and fix the bug that the precondition is avoiding. And in that case, of course, we should remove the precondition so that the bug fix gets properly tested. What happens now? If we run more tests, ta-da, they fail again. Once again, we've got a shrunk example that shows us exactly what went wrong. So in this test, then Wallet 2 tried to start the game, locking with the password hello, and then Wallet 1 tried to make a guess with a correct value. And yet what we see is that the contract instance stopped with an error. Why? Well, again, if we look through the code, through the output, we can see there's a complaint, insufficient funds. Insufficient funds, what does it mean? Why do you need funds to make a guess? You need to have the game token. Right. So you can see that the assertion here that has failed is no, sorry, back up. Let's say the wrong thing. So you have to have the game token to make a guess. Otherwise, the contract crashes. So once again, you might discuss, is this a bug or not? Arguably, you shouldn't submit a guess if you don't have the game token. And so what I'm going to do is so that I can keep going and keep testing, let me write a precondition for guess also. Let's say you may not make a guess unless the wallet holds the game token. And that's going to mean that QuickCheck will never generate this kind of problematic test. And so it goes. And quite often when you use this testing framework, you've got to run through a series of cases where something bad happens. You have to decide, is it a bug or shall I add a precondition? And in this case, there are more problems as well. So this is the final precondition I ended up with. You can see that I also had to check that a guess doesn't ask for more money than there is, because that also crashes the contract. But finally, we end up with preconditions that tell us basically under what conditions the contract works, and then we can run a lot of tests. I like to run 10,000 tests at this point. And now we can see that 10,000 tests pass. That's good. But we also get some statistics automatically. So you can gather all kinds of statistics with QuickCheck, but this library automatically gathers statistics on the number of actions. And what you can see here is that we performed very many more give token actions than guesses or locks. Now, why is this? Well, we defined a precondition so that there can only be one lock per test case, right? And test cases are long sequences of actions. So it's not unexpected that there are very few locks. But guesses? Look, we're doing 10 times as many give tokens as guesses. We're trying to test that the game contract works properly, but most of the time, all we're doing is passing tokens around. So this makes no sense, right? Why are there so few guess actions in the tests? It's because guess has a very tight precondition. Here it is. So for a guess action to be included in a test, you have to have randomly chosen the correct wallet, and you have to have randomly chosen a value that is small enough that it actually, is there locked in the contract. And it's quite unlikely that a guess that you generate will satisfy both those conditions. Now, what you can do, of course, at this point, is you can refine your generator. So here I have changed the code for generating guesses. You can see, once again, I'm using this contract model state so that I can generate something appropriate for the current state. And I am looking up the current holder of the token and then constructing a guess that by construction uses the correct wallet and chooses a value to withdraw in the correct range. So this is going to guarantee that every time I generate a guess, it will satisfy the precondition. And that works. Okay, so this is the distribution that I get now from running the testing. And you can see I'm getting about the same number of guesses as give tokens. And that's pretty good. So that's nice. And I've solved my efficiency problem that previously I was running tests that were wasting a lot of time. Now they're doing much more sensible things. But I know that many people, when they see this code, they ask themselves, well, if the generator guarantees that the precondition of guess is true, why do we still need to write the precondition? Why do we need to check that at all? So this is a very common mistake that people think at this point they can just take that precondition away. You can't do it. Why? Because remember, tests that QuickCheck runs come from two sources. They're generated randomly using the random generator that we've written here until a test fails. And once a test fails, QuickCheck starts shrinking it, which means QuickCheck is constructing lots and lots of smaller tests and running those to see if any of them still fail. And then it reports the smallest one that fails to you. So while we're shrinking, this code is not running. This code is used only to generate the initial random test. But the precondition is, of course, checked while we shrink. So if you don't write this precondition, what will happen is the first time a test fails, the random test will contain valid guesses, but it's very likely that QuickCheck will try a smaller test with an invalid guess in it. Right, perhaps because we've deleted a give token, let's say. And that test will fail because there's an invalid guess. And QuickCheck will say, yes, great, I found a really simple test that fails. This one with an invalid guess. And many people at that point look at the generator code and say, how on earth, why is QuickCheck running this test with an invalid guess? Well, I made sure that I only generate valid ones. Well, the answer is because you didn't make sure that you only shrink to valid ones. And so as a result, if you delete the precondition, then QuickCheck will run tests that make no sense. So you need both. You need the precondition to make sure you only run valid tests, and you need a custom generator to make sure that you test efficiently. But there's another problem here as well, and that is, remember that preconditions are often written to work around bugs. Now, what happens if you later fix the bug and delete the precondition? If you forget to change the generator, then you may think you're now testing the bug fix, but in fact, we are only generating actions that would have satisfied the precondition anyway. So it's actually rather dangerous to do what I did here, because now I'm no longer generating the full variety of actions. So what I would actually do in this kind of situation is I like to have my cake and eat it too. I would write a slightly more complex generator in which I use the QuickCheck frequency function to choose between two alternatives. Most of the time, I'll be smart and I'll generate a guess whose precondition is true, and that will make testing efficient. But some of the time, 1 out of 11 cases here, I'll generate a guess entirely at random. So there will be some invalid guesses in the mix. And as a result, if I fix the bug and delete the precondition, I will still occasionally hit those buggy cases. So then one could go on and gather more statistics here. I gathered some statistics on how often a guess was actually successful. And you can see here that about a quarter of the time the guesses succeeded. I think that's okay. That's a reasonable distribution. Perhaps it might be nice to have slightly more correct guesses, but it's okay to have 3/4 wrong guesses. We're having both kinds of guess quite often. Why are the guesses right a quarter of the time? Because I didn't show you this code, but when I generated guesses, I chose from only 4 alternative passwords so that the guess would be right a quarter of the time. If I had used a random string, then measuring this would have shown me that probably 0% of guesses would have been correct. And then that would mean I wasn't testing the contract very thoroughly. How did I know that I should choose passwords from a small set? Well, it's partly experience in using QuickCheck. It's the kind of thing you often have to think about. And it's partly because I always make this kind of measurement to see how are my tests behaving. And this is one of the lessons I really want to emphasize in this talk. When you're using a property-based testing tool, you must measure the distribution of your tests, and you must tune them so that you get effective and efficient testing. Okay, so there's one more thing. So far, what I've told you about is the state machine testing approach that we've used for many years. But we realized when we thought about testing smart contracts that there's something else you want to know. What we're doing so far is we're taking a random walk in the contract state space and we're testing that nothing goes wrong. Nobody steals your money. Of course, that's important. But with smart contracts, there's something else you care about. Usually, there will be some kind of goal state you have in mind. Typically, a goal state might be when no funds remain locked in the contract. And you want to know not only that nothing goes wrong, nobody steals your money while contract calls are being made, you also want to know that there's always a way to reach that goal. That is, you can recover the money yourself. Right? It's going to be small comfort if nobody can steal your money, if you can't get it back yourself. So we want to test that this yellow path exists too. And at first, that seemed rather difficult to test with QuickCheck, because of course, a random path is very unlikely to end up in a goal state. And even if it doesn't, so what? You make a random path, it didn't reach the goal. All that means is you're not in the goal yet. It doesn't mean you can't get there. So how do we test that this yellow path always exists? Well, we could try generating it automatically. It's very hard to see how to do that. So what we have done is the same thing that we always do when it's hard to do something automatically, and that is give the job to the developer. We have provided a way to specify a strategy for reaching the goal. And what we're going to do is test that your strategy always works. Let's see what that looks like. Here's how we might specify a goal for the game contract. Okay, so I've called it this no locked funds. It's a strategy. It says after any sequence of actions at all, there should be no funds locked in the contract. Okay, so that's my goal. There should be no funds locked in the contract. Of course, it's not going to be true. This test will fail. And if we run QuickCheck, sure enough, we get a counterexample. Once again, it's shrunk down to a very nice, concise example. And what this says here is if you lock you do a lock action, you lock one ADA with this password, then the assertion fails. The locked funds are not zero. Well, of course they're not. We just locked one ADA. So what that shows is that we are not always in the gold state, but we didn't expect to be either. So now I'd like to specify a strategy for reaching the gold state. How do I do that? I just extend this little strategy description. So here's what I have to add. So what's happening here? Well, first of all, I'm going to say that I can choose any wallet to recover the money. Let's call it W, and I'm just choosing any element of my list of wallets. And then I want to recover the money by making a correct guess, of course. And to make a correct guess, I need to know what the current secret is and what the value of the game is at the moment. So let's just read the contract state in the same way as I did before. And now, here's my strategy. I'm going to make this action. Wallet W is going to guess the correct secret. And if I run this test, oh, it failed. Why did it fail? Well, here's what we did. All we did was this witness thing. A witness corresponds to a for all up here. So what this says is we chose wallet 1 to be the wallet to recover the money. And then we tried to make a guess. Wallet 1 is making a guess, and there was a bad precondition. Why was there a bad precondition for this guess? Well, remember the precondition of the guess? The wallet must hold the game token. Does the wallet hold the game token? Not at all. Right? There is no game token. We haven't even started the game. So what this illustrates is that when we write a strategy like this and we say any sequence of actions, this really means any sequence of actions at all, including the empty sequence. So the strategy has to work in all cases. And this strategy doesn't work at the beginning of the game. In fact, at the beginning of the game, there is no money locked. We're already in the gold state. So the strategy doesn't need to do anything. So I just need to refine the strategy a little bit. I can do it like this. Okay, so let's say we only make a guess if there is money to recover. Val is the amount of money in the contract. Does this work? Of course not. Okay, what does this test case show us? Well, if we lock one ADA in the contract, wallet 1 locked it, and then if wallet 2 is chosen to recover the money, and wallet 2 tries to make a guess, there's a bad precondition. Why is there a bad precondition? Remember the game token? Does wallet 2 have it? No, of course not. Wallet 1 has it, and we haven't moved it. So what happened there was that I forgot that I need to give the token to wallet W before wallet W can make the guess. So if we add this, then the test passed, and I could now run a large number of tests. So I'm sure this strategy is not a surprise to any of you. Right? I'm sure you knew that this is how we can get the money out of the contract. But we think there's value in writing it down and testing it. And in particular, forgetting something like giving the token, that's easy to do. But you can develop your strategy in a kind of test-driven development manner here. Right? You write what you think should work, QuickCheck will show you when it doesn't, and then you can just refine it until you get something that works. And in this case, the contract is so simple that the strategy was pretty obvious. But if you've forgotten some kind of corner case, that's the kind of situation in which you could end up with your money locked forever on the blockchain. And it's also the kind of situation that QuickCheck will find for you when you're doing this kind of testing. So we believe that developers know how you should be able to reach the goal. We believe it's not asking a lot of them to ask them to write down the strategy, but we also believe there's a lot of value in doing that and just testing that, you know, they really are right. This strategy really does always work. So we can go on to do things like measure the test distribution here. So I've just added a monitor thing to collect some statistics. Let's record every time there are actually some funds to unlock. It turns out when I added that, I discovered that only 31% of test runs were actually unlocking any funds at all. And the reason for that is that this contract is very simple, and the only thing you do is make guesses and withdraw money from the contract. So it's actually fairly likely that you end up with zero money locked at the end of a random test, which is, fine, but it means that 70% of tests are not testing the strategy because the strategy isn't doing anything. So maybe I might like, when I'm running these tests, maybe I might like to start with a contract that contains more money. No problem. This strategy language lets me extend that very easily. So I can just start off by specifying, let's start a test with a lock action where I've generated the funds differently. And here I've just said, choose funds in the range 1 to 10,000, which is a much larger number than I was doing before. And that leads to a very, a much higher proportion of test runs where there is actually some money to withdraw from the contract at the end of the test. So this strategy language is the thing that is most novel about the work that we've done. And I think it's really exciting. Hitherto, we've tested all kinds of systems in the same way with these state machine models, and we've tested that nothing bad ever happens. We've tested safety properties, and they're important. But with this smart contract library, for the first time, we're also testing liveness properties. We're testing that something good is always possible. And I think this is an exciting new development in property-based testing, and it's going to let us construct all kinds of tests that we never thought of doing before. I expect it to have many other uses. Okay, that's what I had for you. So do we have any more questions?
Thank you very much, John, for your talk. I'm going to give you a little simulated clapping from 188 viewers.
Thank you.
Yeah, there have been a number of questions. I've just saved them if they weren't related to understanding the rest of the talk. I'm just going to go back to them right now. I had a question. With the 10,000 tests, how long did they take to run?
Oh, I don't actually remember. They're running on the contract simulator, the Plutus simulator. So they're not super fast, but perhaps they might have taken 10 minutes.
Okay, thanks.
Time for a cup of coffee.
Next question. Is there any symbolic execution of actions underlying these examples, or is there a different state machine testing abstraction than the one implemented in QuickCheck, Hedgehog, etc.?
The state machine testing abstraction is similar to the one in QuickCheck, Hedgehog, and so on. There isn't any symbolic execution going on. Symbolic execution could be interesting to try, of course. Symbolic execution of Haskell wouldn't be entirely straightforward. So no, it's working in the same kind of way as other property-based testing tools that use state machines. The really novel thing here is the strategy language.
Okay, thanks. Then I have a question. Could these preconditions be represented at the type level in a practical way? How would you evaluate the trade-off of doing so?
So in this case, some of the time we were using preconditions to work around bugs in the code. So the preconditions were, it's important to be able to generate tests that provoke bugs in the code. So you don't want to rule them out at the type level in the tests unless you also rule them out at the type level in the actual endpoint invocations. And I guess it's in the nature of bugs that they weren't ruled out by the types. I think could you
I don't know. Could these preconditions be represented at the type level? Let me see who. Maybe this person was referring to a stronger type system than the one currently there. I don't know. Would you like to?
Well, so you would need to keep track of the state of the contract at the type level. And so if you used, what are they, indexed monads, I think. So you couldn't use standard monads. You'd need to use some richer notion of monad. I think the Haskell's type system is rich enough nowadays that you probably could capture some, at least, of these preconditions at the type level. But then you're depending on the person writing the contract to do that when they construct their API. I think the API that Plutus contracts present at the moment is not as strongly typed as that. So in practice, I don't think you could do it at the moment.
Okay, thank you. I now have some more general questions. So a question I had, how do the properties we are testing look like? So what do they look like? I guess this is a general question regarding what type of properties there are. Okay, so in this case, the way that I was specifying the properties that we were testing was by writing that next state function, because the next state specifies how the contract state should change, but also how tokens should move between wallets. And then at the end of a test, there's a generic property that looks at the model and looks at the actual result and checks that the actual wallets contain the tokens that the model predicts they should contain. There are some other things as well. So there are checks that the contracts didn't crash, for example, that the contracts didn't hang. There's a variety of things you can look at that are kind of generic correctness properties. But the key thing we're testing, based on the model, is that the tokens end up where they should. The money ends up where it should. And so the next state function specifies where it should end up, and some code that's part of the framework checks that it actually does. Thanks. So the property, concretely speaking, the property that you give to QuickCheck here is a property that is exported by the framework. And when you test that property, what it does is generate tests using the callbacks that you have supplied in the contract model class and running them against the the actual contract, and then checking the context of wallets against what the contract model says they should contain. Great, thanks. Let me just scan through the forum again if something has come in that time. What kind of use cases are there for smart contracts? I guess this is more of a smart contract question. Yeah, what are they for? Well, for example, different kinds of auctions can be expressed as smart contracts. So that's one common example. There are a number of smart contracts provided in the Plutus playground. There's something called Prism, which is a certification server. So you can get a kind of identity certificate that you can present to validate yourself. The DAO attack was on a crowdfunding contract where anybody could call the contract to contribute to the crowdfund, and then when a proposal would be made for how to invest the money, then everybody who had submitted money could submit, could vote yes or no, or also vote to split off a part of the crowdfund into another fund that rejects that particular application but may accept others. And it was actually in that splitting off functionality of the contract that the bug was that allowed the theft of the $60 million. So there's a variety of things. There's also something called CryptoKitties, which are kind of genetic codes for kittens, not real kittens, obviously, but from the genetic code, you can render an image of your kitty, and then you can breed your CryptoKitties with other CryptoKitties. And then there's a partially random genetic crossover operation that is applied to generate new CryptoKitties. And every now and then, a CryptoKitty is born with some
valuable mutation. And people collect these things. So, you know, they're non-fungible tokens that you can own. And you can invest in breeding CryptoKitties and trying to develop new exciting ones. You know, by sheer chance, some of these exciting mutations will happen from time to time, and then maybe it'll breed true. And CryptoKitties was for a while the most active contract on the Ethereum blockchain. I understand it almost brought the infrastructure down. So, you know, you can do all kinds of things with smart contracts.
Thanks. I have another question. How would one select the number of test runs for a smart contract, given the consequences of edge cases can be very costly?
Yes. So by default, QuickCheck runs 100 tests. And I would say in any real situation, you need far more than that. Now, how many tests you need depends very much on the distribution of random tests. So a couple of times during the talk, I showed you how I measured statistics about my tests. And usually I measure statistics, I see something I don't like, and then I tune the generation. And if you have well-tuned generation that is hitting every part of your code, you know, reasonably often, then maybe you don't need an enormously large number of tests. If your generation is bad, so that some critical part of your code is hit, let's say 1 in 1,000 tests, then in order to test that part of the code well, you need to run millions. But there's no general answer to that question. I think the best answer I can give is measure your tests, measure the outcome. How often do various different kinds of things happen? Look at the code coverage of your code when you run tests, right? If you see there's parts of your code that are not being covered, that tells you that you need to change the distribution of tests to hit those parts of the code more often. But once you've got a good distribution of tests, I mean, I use 10,000 tests often as a, you know, a kind of round number, because generally that will run fairly quickly. So I'm not sitting waiting a long time. If I've got something important, I'll run 1 million tests. Or, you know, at Cubic, when we're testing important stuff, I'll start an overnight test run that will run 10 million tests, maybe. And there are bugs that you only find once every few million tests. So, you know, how many tests should you run? Well, how much do you care that your code is correct? But buying a beefy parallel computer helps a lot with this.
Great, thanks. Another question. It seems that QuickCheck shrinking on the first failing test leads to quickly adding preconditions that could mask actual errors in the smart contract. Is there a way to have QuickCheck not shrink on the first test case as a way to find a multitude of combinations that could lead to failures?
Well, now, I think I showed you preconditions that I added in some cases to avoid nonsensical tests and in other cases to work around bugs. So the latter kind of precondition says, don't test this. We know it doesn't work. Right. So it's not really true to say that that precondition is masking another kind of bug. Right. It's not masking anything. We know it's buggy. So, of course, if you tighten your preconditions too much, if you write preconditions that won't apply when the API is actually used in practice, then you may fail to find bugs. So you have to be careful. When you add a precondition, you have to think to yourself, you know, is this really a precondition that I believe should hold of real use of this API, or is it something I'm adding to get around a bug? And quite often we actually will parameterize preconditions on whether or not a bug is fixed. So, you know, maybe in a header file somewhere, we'll have a list of bugs and whether they're fixed or not. And then the precondition will apply only if the bug is not fixed. And so we try and be systematic to make sure that when we have those kind of bug preconditions, that they get turned off once the bug is fixed. But otherwise, the good thing about adding preconditions like that is just that they avoid masking bugs. So if you have a bug that QuickCheck finds, once in every 100 tests, and there is another bug that QuickCheck finds once in every 10,000 tests, then it's very unlikely that you will find that other bug at all, because every time you hit it, there's a good chance that during shrinking, QuickCheck will hit the more common bug and report that one instead. Now, I think the question did mention shrinking, so maybe the questioner is wondering, what if you turn shrinking off? Could that mean that that you would find the other rare bug instead of shrinking down to the common one? So you can turn shrinking off. It's a bad idea, because what happens is you get very large failing cases that are very hard to diagnose, and most of them will fail because of the common bug. So you're setting yourself up for doing a lot of work analyzing test cases, which in almost all cases will be wasted. Don't do that. You add the precondition instead, so that QuickCheck avoids failing for that reason. And then when you hit the 1 in 10,000 tests bug, it will shrink to the smallest case that doesn't fail for the easy reason, but actually fails because of something, the thing you're actually looking for. So making shrinking work well for you, that is key to getting value out of property-based testing.
Great, thanks. I have another question here. Is my understanding correct that the essence of this type of testing is to check that the actual system behaves the same as the model does? So it executes both and compares the results for many different inputs. In other words, is this not typical? This is not typical property testing, but it uses property testing as an engine.
Yes, this is using property-based testing as an engine. There are other ways in which you can use property-based testing, but for this particular example, indeed, what we're testing is that the actual transfers of tokens correspond to the transfers in the model. Now, the model may nonetheless be very much simpler than the actual implementation. But yes, in this case, we're testing that they behave in a comparable way.
Great, thank you. That was the end of the questions in the forum. Thank you again for your answers and your talk.
Okay, thank you very much. It was fun. Enjoy the rest of ZuriHack, everybody.
Yeah, thank you, everyone, and see you at the next session. Bye-bye.
Bye-bye.